Okay, good afternoon once again to all of you. Now, in this afternoon class, I will just mark for you all what is important from the chapter water. Okay, from this chapter hydrogen. Now, the next topic is water. In the morning class, I was discussing about hydrides. Okay, till this molecular hydrides, polymeric hydrides is not required. Only uses are required. Now that was on page number 568. Now you can turn your books to page 569. Page number 569 for water. 569 for water. Now here please note that in the first paragraph with regard to the introduction of water, we know water is a universal solvent. So there are so many factors which makes it a universal solvent. Okay. Now next to oxygen over here, water is most essential to all living creatures. It is also essential for all types of vegetation. Okay, it is most abundant in the biosphere. The total global water supply is estimated roughly equal to so much volume, 1.4 power of 9 kilometer cube. Out of this, 97.3% is held by the oceans and inland saline water bodies. The fresh water amounts to only 2.7%. Okay, all these things are there. So this is the first paragraph. After that, water is a unique substance from chemical point of view. That is important for us. It shows very interesting and unique properties. It is an oxide of hydrogen and consists of one part of hydrogen and 8 parts of oxygen by weight. This is important sentence. And possesses molecular formula H2O. So we will discuss about this in detail. Now, structure of water molecule and its aggregates. Now, with if you look at the formula of water, it is H2O. Now we can see from the formula there are two hydrogen atoms and one oxygen atom. Okay. Now this is something which I've already learned from the VSEPR theory. The two bond pairs and the two non-bonding pairs, that is called lone pairs, present on the central oxygen atom orient orient themselves in a tetrahedral geometry as shown in the figure over here. Now, consequently, the water molecule has an angular or bent structure, or we can say it has a V-shaped structure. The repulsive interaction of lone pairs and bond pairs decreases the bond angle from 109 degrees 28 minutes to finally the bond angle is lowered to 104.5 degrees. The two OH bonds are equal in length and the OH bond length is 95.7 picometer. Oxygen is highly electronegative and has a strong tendency to pull the shared pair of electrons towards its own side because it is electronegative. This results in the development of polarity in the water molecule. Okay. Now, as a result of which we can see dipole moment of water molecule is found and whose value is 1.85 diopter, which confirms the its planar nature. Okay, so that is the structure of water molecule. Now, if you talk about the liquid state of water molecule, the water molecules are held to each other by intermolecular hydrogen bonding, as shown in the diagram over here. Now, if you see, each oxygen of one water molecule is linked to the hydrogen of the other water molecule, other neighboring molecules, which results in intermolecular hydrogen bonding. Okay, now that is in the liquid state. Now, water consists of aggregates of varying number of water molecules held together by hydrogen bonds. So here, some free water molecules also exist. In fact, there is a dynamic equilibrium between the aggregates of water molecules and free molecules. The free water molecules continuously form aggregates which continuously collapse and change into free molecules. The presence of aggregates of molecules due to hydrogen bonding affects several properties of water to a considerable extent. This existence of water in the liquid state is exceptionally high boiling point as compared to other hydrides of the elements of group P16 And many more unique properties of water may be attributed to the presence of hydrogen bonding, which is intermolecular. Okay. Now, if you move further in the solid state, the water molecules come still closer and get arranged tetrahedrally, as already discussed earlier. The solid form of water, that is ice, exists in different crystalline form depending upon the conditions used for freezing water. The structure of normal hexagonal ice is shown over here in this figure. This is the structure of normal hexagonal ice solid state structure. Okay. In this type ice, each oxygen atom is tetrahedrally surrounded by four other oxygen atoms through a hydrogen bond. Each hydrogen atom is covalently bonded to one oxygen atom and is linked to another oxygen atom by a hydrogen bond. This type of packing leads to an open cage structure with large open spaces. This is why the density of ice is less than that of water and it floats on water. So this is the main reason. That's a normal external structure with lot of spaces in between. Lot of spaces are there. That makes the density of ice lesser than that of liquid water. Therefore, we can say over here, this type of packing, this is why the density of ice is less than that of water and it floats on water. This property is very helpful for the animals living in water. The floating ice prevents or delays the freezing of underlying water. Therefore, sea animals can survive even in severe climates. Okay, so that is one point you have to remember. Then moving to the physical properties. If you look at the physical properties, many of the physical properties of water are peculiar and unexpected. Some properties are discussed over here in this table. Comparison to deuterium oxide, that is heavy water, D2O and H2O. Okay, you can just say comparative. They are almost similar. They are almost similar. Now here in this paragraph, the freezing point, boiling point, heat of fusion, and heat of vaporization of water are much higher as compared to the hydrides of other elements of group 16. The abnormality in this property is due to the presence of intermolecular hydrogen bonds in water. So this is the main thing over here. Intermolecular hydrogen bond is the main cause, main reason for the abnormality in these properties like melting point, boiling point, heat of fusion, heat of evaporation, and so on. Now the abnormal physical properties of water play a very important role in the biosphere also. The heat of evaporation and the high heat capacity of water are responsible for the moderating influence of water on the climate and the body temperature of living organisms. The high boiling point of water is helpful to keep it in the liquid state at ordinary temperature. Otherwise, it would be volatile. Okay. Now, water is an excellent solvent. It is a universal solvent because of its polar nature, polar covalent nature, as well as dipole moment. Even the covalent organic compounds such as alcohols which contain OH, carbohydrates dissolved to a considerable extent in water due to the ability to form hydrogen bonds with water molecule. That is again intermolecular hydrogen bonds. Now, due to its great solubilizing action, it provides an excellent means to transport ions and molecules to plants and animals needed for their metabolism in plant chemistry. Okay, now coming to the chemical properties of water over here in this chapter, there are certain reactions of water which behaves as an acid, it can behave as a base, it can behave as an oxidizing agent, it can behave as a reducing agent, and as well as a ligand in coordination chemistry to certain metal ions. Here, water exhibits a versatile range of chemical behavior. That's why we have got a number of reactions with regard to water. Stability. Water molecule has a very high thermal stability as is indicated from its high negative heat of formation. That means the heat of formation of water is very negative, minus 285.9 kilojoules per mole. So at 1500 Kelvin, it dissociates only to an extent of less than 0.02%. But at 2270 Kelvin and 180 MP, its dissociation is about 0.6%. That means its heat of what you call this formation, it is highly negative. It has very high thermal stability. Then ionization. The ionization of water is not much. It has a small but measurable electrical conductivity due to the following equilibrium. So, two molecules of water at equilibrium, they produce hydronium and hydroxyl ions, which we have seen from the chapter chemical equilibrium. So the ionic product over here, we know it's already this much at 298 Kelvin. Amphoteric nature. Amphoteric nature means it can behave like an acid, it can behave like a base or an alkali at the same time. Now, although water is neutral towards litmus pH 7 at 298 Kelvin, yet it acts both as an acid and as a base, and thus shows amphoteric nature. It acts as a base towards acid stronger than itself and as an acid in the presence of a base stronger than itself. So, example is here. So, if you put hydrochloric acid in water, it is behaving like a base. If you put uh, ammonia in water, it will behave like a acid over here. So this reaction is important over here, amphoteric nature of water. Okay. Then oxidizing and reducing nature. Water can act both as an oxidizing as well as a reducing agent. It acts as an oxidizing agent in its reactions with active metals. For example, if you look at metals, reactive metals like sodium, potassium, magnesium reacting with water in various forms, either in boiling form or steam, it is liberating hydrogen gas. But when you react with highly electronic elements, water acts as a reducing agent. Here, it is reducing, okay, in the presence of sunlight or ultraviolet light to produce oxygen gas, or oxygen gas. Okay. Then hydrolyzing nature. Water can hydrolyze several halides, hydrides, carbides, nitrides, phosphides. Examples are given over here. Hydrolyzing nature, hydrolysis, addition of water to them. So here, silicon tetrafluoride, it is forming orthosilicic acid, H2SiO4 and hydrochloric acid. Calcium hydride, calcium hydroxide and hydrogen. Calcium carbide, it is hydrolyzing to give acetylene from organic chemistry with calcium hydroxide. Aluminum carbide, same thing, methane. Magnesium nitride, ammonia. Aluminum nitride, ammonia. Calcium phosphide, it is forming phosphine. So these are the reactions in which water is showing its hydrolyzing nature. Hydrolyzing means water is getting added to this compound to form either hydroxides, or in the case of silicon tetrafluoride, it is producing orthosilicic acid. Then formation of hydrates. Okay, water reacts with certain metal salts to form compound known as hydrates. Depending upon the mode of linkage of water molecules, we have following three types of hydrates. The first one over here, coordinate bonds, where you will find coordinate bonds. These six, these six water molecules are linked to iron by means of coordinate bonds like this. Water is here, water is here, okay, that way. 1, 2, 3, 4, 5, 6. So in coordination chemistry, and Cl minus is there. Okay, so this is one type of bond where you will find in coordination compounds. In some hydrates, water molecules get attached to certain oxygen containing anions through hydrogen bonds like copper sulfate, like crystals of copper sulfate, where you see CuSO4 dot 5H2O. This is a weak chemical combination over here. In some hydrates, water molecules occupy the interstitial sites. The empty spaces is occupied by water molecules. Like for example, barium chloride, crystals of barium chloride, you will find water molecules in the lattice of barium chloride solid. Okay, so these were some chemical properties of water molecule. Now there are two types of water, hard and soft water. Okay, now here we learn about softening of water, hard water. Water which is obtained from natural sources is largely used for washing purpose. We know that. Water obtained from a particular source may or may not produce a high lather with soap. Lather means foaming with soap. Generally used for washing purpose. Hence, it is important to study the behavior of water obtained from natural source towards soap solution. On this basis, water can be classified into following categories. So let us look at the different categories. One is soft water and hard water. Now you have to remember the meaning of soft water. Water which produces lather with soap solution readily is called soft water. Okay, that is soft. It doesn't contain any carbonated carbonates of calcium or magnesium. That's why it is soft. It can lather easily with soap. Distilled water, rainwater are some examples of this type of water. Whereas hard water, water which does not produce lather with soap solution readily is called hard water. Seawater, it contains dissolved salts, okay, calcium, magnesium, all those things. And water of some rivers, water from some wells, etc., are common examples of hard water. Now, what is advantage? Let us see. What is the cause of hardness of water? Now, natural water contains many salts dissolved in it. These salts get dissolved in it when it passes over rocks or through the various underlying layers of earth. The most common salts that dissolve in water are bicarbonates, chlorides, and sulfates of calcium and magnesium. Now, the presence of these salts make water hard. Thus, hard water may be defined as the water which contains what? Bicarbonates, chlorides, or sulfates of calcium or magnesium. So, water containing any of these salts does not produce lather with soap readily. This can be explained below over here. Now, soaps are what? Sodium or potassium salts of higher fatty acids like palmitic acid, stearic acid, etc. Thus, the compounds like sodium palmitate, sodium stearate act as soap. When hard water containing calcium ions and magnesium ion is treated with a soap solution, a precipitate of the calcium or magnesium salt of the corresponding fatty is obtained as given below. Don't learn this reaction, okay? Thus, with the use of hard water, soap gets precipitated in the form of calcium and magnesium salts, which are insoluble in water. That's why there is no lather. Hence, no lather is produced till all the calcium or magnesium ions get precipitated. This results in more consumption and hence in the wastage of soap. Soap gets wasted. So that's why in the like plains and all, if you're using underground water, well water, the well water contains, chlorides, it may contain bicarbonates, it may contain sulfates or calcium carbonates, bicarbonates, magnesium carbonate, bicarbonate, which do not lather with soap. That's why they cause wastage of the soap. A soap gets finished off faster in plain areas where the water is hard. Thus, with the use of hard water, soap gets precipitated and there is a lot of wastage. So that's why we need to remove the hardness of water. Now, let us see what are the different types of hardness. One is temporary hardness. Now, when I'm talking about temporary hardness, this is due to the presence of bicarbonates of calcium and magnesium dissolved in water. So, temporary hardness is caused by the dissolved carbonates and bicarbonates of calcium and magnesium. Okay, the hardness due to the bicarbonates of calcium and magnesium is termed as temporary hardness because it can be easily removed just simply by boiling the hard water. If you boil the hard water, then the hardness can be removed, provided the hard water is because of the bicarbonates of calcium and magnesium. Otherwise, the water is termed as permanent hard water. Now, the permanent hard water is due to the presence of chlorides. If there are chlorides and sulfates of calcium and magnesium dissolved in water, it makes the water permanently hard. This cannot be removed easily just by boiling and hard water, hence it is called permanent hardness. So it is difficult for us to make permanently hard water into soft water. So we have to apply certain processes. Now, how to soften water? We know the process of removal of calcium and magnesium ions from hard water is termed as softening of hard water. There are several methods, so we'll discuss the methods quickly over here. The first one is removal of temporary hardness just by boiling. If you boil calcium bicarbonate or magnesium bicarbonate present in water, they get converted to calcium carbonates and magnesium carbonate, and water gets separated over here. So the water is now soft. The insoluble carbonates settle at the bottom and can be removed by filtration or by decantation. The water thus obtained is soft. Now, the other method is called by Clark's method. In this method, a calculated amount of calcium hydroxide, that is called milk of lime, is added to the temporary hard water. This treatment converts the soluble bicarbonates and insoluble bicarbonates get precipitated and can be removed by again filtration. So this use of milk of lime, which is calcium hydroxide chemically, it is called Clark's method. So there are two methods to remove temporary hardness of water. One is by boiling, and if you can't provide boiling, then you have to provide milk of lime being added over there to remove the hardness. Now, how to remove the permanent hardness of water? The permanent hardness can be removed by any of the following methods given below. The first one is by adding washing soda. Washing soda is Na2CO3.10H2O. Na2CO3.10H2O. This is washing soda. So if we add washing soda, the soluble chlorides and sulfates of calcium and magnesium are converted into their insoluble carbonates, which get precipitated and may be removed by again filtration. So use of washing soda to remove hardness, it is called removal of the permanent hardness of water. This you have to remember. Okay, so there can be questions asked on this. So using when we are using washing soda to remove hardness of water, it is the removal of permanent hardness in water. Okay, now after that, the equation you can see over here, calcium chloride and the sulfate treated with washing soda to make it insoluble magnesium and calcium carbonates, okay, which can be filtered. The next method is called Calgon process, a very interesting, quite interesting process over here. This is a convenient method to soften hard water, is to render calcium and magnesium ions ineffective instead of removing them from water. This is done by addition of a salt over here. Sodium polymetaphosphate. Remember the formula. Its formula is NaPO3N. This small n can be, it has to be more than 2, 3, 4, 2, 3, and so on. Okay. Now, where the value of n is somewhere as large as 1000. However, sodium hexametaphosphate, that is NaPO36 or Na2Na4PO36, is generally used for this purpose. So, remember, we use normally sodium hexametaphosphate, whose formula is Na2O36. Remember this formula. Now, here, when hard water containing calcium and magnesium ions is treated with calgon, complex soluble salts like this are obtained. These salts are ineffective. They do not change the properties of water. So, they can remain in the water, but they will not interfere with anything else. The complex salts thus formed remain dissolved in water. They do not cause hardness because the ions which cause hardness, that is calcium and magnesium, are not free. They have been trapped by whom? By calgon. Calgon. Now, this sodium hexametaphosphate, it is called calgon. The market name, the trade name is calgon. Okay. Now, the other method, which is also generally applied, it is called ion exchange method, which is used in purifiers, which is installed in houses. This is the most modern technique widely used to soften hard water over here. In this technique, calcium and magnesium ions which cause hardness are exchanged by those cations which do not cause hardness. The exchange of ions is done with the help of certain substances called ion exchangers. Following two types of ion exchangers are generally used for this purpose. One is permuted process, that is inorganic cation exchanges. Okay, the reactions you can see over here. The calcium and the magnesium, they are reacted with sodium zeolite. Sodium zeolite, permuted. Okay, and this permuted combines with to make it calcium zeolite and magnesium zeolite, and the ions, sodium ions, the soluble ions are produced. Whereas the calcium and magnesium, they are trapped. They are trapped. They are trapped by the zeolite. Okay, that is how we remove the hardness by the ion exchange method. Okay, now as the process continues, permutate gets exhausted due to its conversion into calcium and magnesium zeolites. It takes about 12 hours for the permutate to get completely exhausted. Therefore, after a continuous use for 12 hours, it must be regenerated. This is done by percolating a 10% solution of sodium chloride. So what we have to do is, to this calcium zeolite and magnesium zeolite, we add 10% sodium chloride solution to regenerate the salt. Okay, and then after this treatment, the packing is washed with water to remove the chlorides of calcium. This calcium and magnesium chlorides are removed by washing, and regenerate permutate is now ready for use again. Okay, now there are other methods also, like organic ion exchanges also used to what we call remove the permanent hardness in water. Over here, recently some complex organic compound known as resins have been introduced to remove all minerals from hard water. They remove all cations and anions except hydrogen and hydroxide ions from hard water and make it completely demineralized. So this is also one method. Do not read the next paragraph after that. Now, After that, this is all about the chemistry, about the removal of what you call calcium and magnesium ions from hard water to make it into soft water. So this is the organic part over here. Now coming to heavy water, deuterium on page number 574, deuterium oxide. Heavy water is the oxide of deuterium. It was discovered by Urey, an American scientist. It occurs to an extent of 1 part in 6,000 parts of ordinary water. How to prepare? Preparation of heavy water. This, if you look at the syllabus for the preparation of heavy water, it is not mentioned. It is not mentioned at all in the preparation of heavy water over there. But only the what do you call what is heavy water, that is more important in this part. Okay. Now properties. This should leave it out. This should leave it out. And coming to the properties that is required. Heavy water is colorless like water, odorless and tasteless mobile liquid. Almost all the physical constants, example specific gravity, melting point, boiling point of water, are higher than those of ordinary water because its what do you call mass number is higher. It has a mass number which is higher than what do you call hydrogen, uh, protium, deuterium, tritium, because deuterium gives heavy water. If you look at the chemical properties, the reactions are almost similar. Reaction of heavy water with sodium liberates D2, with calcium liberates D2, like hydrogen. Electrolysis. If you pass electric current through this heavy water, it produces deuterium molecule at the cathode, oxygen at the anode. Similarly, if you react with metal oxides, reaction is same. Sodium deuteroxide, calcium deuteroxide. Reaction with non-metal oxides, same thing over here. Deuterium oxide over here with sulfur trioxide, phosphorus pentoxide, nitrogen, dinitrogen pentoxide. It is producing deuterosulfuric acid, deuterophosphoric acid, deuteronitric acid. Okay, but these are not so important. Okay, not so important. Okay, reaction with carbides also reaction similar like water. Okay, same thing here also deuterio ammonia. Okay, this is not so important. Leave it out. Hmm. Then moving to the next slide over here. Uh, this part I think you can leave it out. This part now coming to the uses of heavy water. Uses are required. It's very important. The first one is heavy water is used as a moderator in nuclear reactions involving the fission of uranium, where it slows down the speed of neutron ejected in the fission process. So, use of heavy water is where in controlling the nuclear reactions during the fission of radioactive uranium. It is used as a tracer in the study of reactions occurring in living organisms. Okay, so what are the reactions happening? So if you instead of water, if you inject over there D2O, that is heavy water, we can follow its movement in the system, in the mechanisms happening in living organisms and find out what is the movement, how it is used up. Okay, so that is how we can use as a tracer. It is also used for the preparation of deuterium, that is D2. Okay, so these are the important uses of hard water. Okay, now the next thing we are supposed to do is in the syllabus, as according to the syllabus, is hydrogen peroxide, which is the most important part of this chapter. Hydrogen, because plenty of chemical reactions have been directly asked from this part of the chapter. So they will ask you write down the chemical equation for the preparation of hydrogen peroxide from sodium peroxide, that is in the laboratory, so here if you see hydrogen peroxide with the formula H2O2, H2, 2 hydrogen, 2 oxygen, H2, okay, H2O2, like this. Okay, now here in the lab, you can prepare from sodium peroxide. When a calculated quantity of sodium peroxide is treated 20% of ice cold sulfuric acid solution in small amounts with constant stirring, we get hydrogen peroxide, which is highly unstable. Remember that. Now, the resulting solution is further cooled to 271 below 0 degrees Celsius. When sodium sulfate crystallizes out at sodium sulfate tends to global salt, these are removed by filtration. The resulting solution, whatever is left, contains 30% hydrogen peroxide along with some dissolved sodium sulfate. This solution is generally used for bleaching purpose. So remember, the solution which is obtained after removal of this Na2SO4.10 acetate is global salt crystals. It is used for bleaching purpose. The next method is from barium peroxide. We can use barium peroxide crystals reacting with sulfuric acid dilute, very dilute sulfuric acid, to obtain hydrogen peroxide also. The precipitate of barium sulfate formed is filtered off. The resulting solution contains about 5% hydrogen peroxide. Anhydrous barium peroxide should not be used in this purpose because its reaction is slow and ceases after some time due to the formation of protective layer on the precipitated barium sulfate on it. So that's why you have to make sure that anhydrous barium, what you call, peroxide, is not used. The next method is by the action of phosphoric acid. If you react phosphoric acid with barium peroxide, okay, then it is a better method, of course. So we get hydrogen peroxide. Okay, instead of dilute sulfuric acid, we can use phosphoric acid as well over here. Okay, now here in this method, all the heavy metal impurities are thrown out as insoluble phosphates, which can be filtered. Therefore, the resulting solution of hydrogen peroxide does not contain heavy metal ions which promote its decomposition. Okay, hence hydrogen peroxide prepared by this method is much more stable. Okay, now the next one is manufacture over here. What do you call, from manufacture of hydrogen peroxide, this is there given but which is not required. So this, I think you can leave it out, this part you can leave it out. Okay, then concentration and storage of hydrogen peroxide solution. This concentration also we will not discuss because this is not in the syllabus, is not required. Okay, then regarding the properties, these properties of hydrogen peroxide, I will discuss the physical properties and the chemical properties we will discuss in the next class tomorrow. Okay, so with this, I would like to end my class here only, but just hang on because I need to record your attendance. So in the next class, I'll be doing with you all properties of hydrogen peroxide on page number 578. Okay, so just hang on. Your attendance is downloaded. Okay, so thank you so much. Have a nice day.